If it has a higher velocity, then it's probably a little, maybe closer to the speed of light. Then the definition of refractive index was c over the velocity. So it means the refractive index will be inversely proportional to the speed of the light. So if it's moving real fast, refractive index will be lower. If it's moving slower, refractive index will be higher. So because of that, it'll make sense that when I start talking about the indicatrix figures, that they will be inverted compared to this. Okay, so this happens to provide you with a diagram of positive and negative optic sign crystals, uniaxial crystals, but only for ray velocity surfaces. And what you'll see is that when I flip over to the indicatrix figures, something like this will end up looking like the positive optic sign, and something like this will end up looking like the negative optic sign. So that's why it's important for you to be able to go back and forth between the idea of ray velocity and indicatrix. That said, the ray velocity is like a little easier to think about because it's how fast the speed of light is going. It's like how fast is the car moving, etc. Whereas the indicatrix is what's the magnitude of the refractive index in this particular direction. So you have to think another step in your head to understand the indicatrix figures a little bit better. Okay. I already did this. Like I said, these are the points at which epsilon prime and omega experience the same refractive index. Okay, that's where the ellipse and circle meet. Okay. U and O ray are the same. Epsilon prime is omega. So this is actually also the direction of the optic axis. Okay. Notice that the O ray always vibrates perpendicular to the optic axis. So over here, it shows you this double arrow over here. That's the optic axis of the crystal. Okay. So if you happen to have a situation where, let's do a little pretend here. Here's my crystal, and let's say, and it isn't the case, but let's say, for example, the optic axis of the crystal was up and down, like this, okay? Just like you see over there. If that were the case, on your microscope, the light's coming from the bottom, okay? If I had this crystal, and it's huge, but you get the idea. If it were like a little version of it, on the stage of the microscope, then the light coming through the polarizer is only vibrating east-west, okay? That light hits the bottom of the crystal. That light splits into two rays that are vibrating perpendicular to each other. However, you have a situation where no matter how you rotate this, the omega is always being experienced, right? Because omega vibrates perpendicular to, so if that's the optic axis, then this is the vibrational mode of omega. This way, that way. Every direction perpendicular to the optic axis is the direction that omega will be vibrating, okay? So it's something to start relating to. Okay. So the three-dimensional ray velocity surfaces can be generated from, I already mentioned this, like what you saw were two-dimensional versions where it was a circle and an ellipse, but the idea would be if you rotated the circle around in 3 dimensions, it would be a sphere, and if you rotated the ellipse around in 3 dimensions, it would be an ellipsoid of revolution, okay? So that's what this means. Okay, ellipsoids of revolution, and the O-rays are spheres. Okay. So, and I kind of already jumped ahead with this when I showed you the earlier exact same images. So this also demonstrates a property known as optic sign. And when you look at optic sign, once again, you can see it represented with ray velocity surfaces here. But you can also, if you memorize the definition, the optic sign, if epsilon is greater than omega, it's a positive optic sign. If epsilon is less than omega, then it's a negative optic sign. Now remember, epsilon and omega are the refractive indices. The speed if epsilon is greater than omega, then epsilon has a higher refractive index, right? I mean, epsilon is a higher refractive index. Epsilon represents one of the principal refractive indices being experienced by the light rays. Omega representing the other refractive index. And remember, epsilon is a particular, like either a maximal or a minimal value, because omega is the same no matter what, right? That's why it's ordinary. Epsilon or epsilon primes can be experienced by the light rays that are vibrating perpendicular to the ordinary ray. So in this particular situation, you see that, let's look in this direction. The light starts here and it heads to the right. The light that experiences the extraordinary ray doesn't go as far as a light that experiences the ordinary ray. The ordinary ray was faster, right? If the ordinary ray was faster and the extraordinary ray was slower, that means epsilon had the higher refractive index. Higher refractive index, moving more slowly. Okay. Omega, lower refractive index, moving more quickly. Epsilon is greater than omega in this particular, and it makes sense over here and over here. Okay, either the light going to the right or the light going to the left. The extraordinary ray did not go as far. Okay, whereas over here it's the other way around. You have your circle inside of the ellipse, and the light ray that starts right at the crosshairs over here, it heads to the right. That particular set of light rays vibrating perpendicular to each other. The ordinary ray is experiencing omega, and it only went this far in a unit of time, whereas the extraordinary ray went further in the exact same unit of time. So as a result, you can see that, okay, so the extraordinary ray, the epsilon it was experiencing must have been a lower value for refractive index in order for it to have moved faster and gone further. Okay, so omega over here must have had the higher refractive index. It was moving more slowly. Remember, velocity and refractive index are inversely proportional, and this is based on the refractive index definition. Okay, so what this means is that omega must be greater than epsilon. So just like I said, omega greater than epsilon, negative optic sign. Epsilon greater than omega, positive optic sign. And this is just the way, this is just the demonstration of it with ray velocity surfaces. Later on, when we're dealing with indicatrix figures, we're going to see that, okay, because the indicatrix figures directly measure refractive index in any particular direction for epsilon and omega, then we can see, okay, well, the epsilon refractive index is a larger diameter than the omega diameter on the indicatrix figure. I'll show you that in a little bit. I will have those figures available in the laboratory for you guys to work with, and they are a big help in understanding these things, because otherwise you're trying to imagine it in your brain. At the very least, if you start working with the three-dimensional indicatrix figures and beginning to understand which one's uniaxial, which ones are biaxial. I see a circle over here. That must be the ordinary ray for the uniaxial, right? The ellipse must represent the different possible directions for the extraordinary ray. And then by the time you get to the biaxial, it gets even more complicated. Okay. So this is kind of what I just mentioned before. Okay, same thing, but makes sense, but you have to think of it. You have to look at it. You have to think, what is this? Is it a ray velocity figure, or is it an indicatrix figure? Because it's going to be inverse depending on which figure you're looking at. That's important. Is it ray velocity or indicatrix figure? Based on that, am I seeing a circle inside of an ellipse inside of a circle? And think of it, if it's, for this, it's a ray velocity surface. So it's how fast the rays are moving. And the faster the velocity, the lower the refractive index. So I keep saying it over and over again, but like I said, these are things where you can see the images, and I want you to be able to make the interpretation based on the definitions. And you have to basically memorize a definition of positive optic sign means that epsilon is greater than omega. Okay, that's the definition that you have to remember, just have to memorize. Okay, so when omega is less than epsilon, let's see. Yeah, omega is less than epsilon, or epsilon is greater than omega, same thing, positive optic sign. Okay, and this is the flip side, where epsilon is less than omega, negative optic sign. Okay. Okay. The optic sign is the sign of the difference between epsilon and omega. So if you want to think of it this way, epsilon minus omega, well, if epsilon is greater than omega, and you can think of it in actual numerical terms. In the Crim lab, we have particle atlas, and they've made photocopies. The particle atlas has been beaten up over for like 30 years probably. So the book is falling apart. So my staff has made photocopies of the relevant pages that you need. Not only that, but Crim Research Institute actually has an online particle atlas. And it's free for anyone to use. You just have to go in and register for free. And when you do that, you can access information about all kinds of materials, particles, but particles including hairs and fibers, like you'll be working with, and mineral particles, which you will be working with. So you will be using the particle atlas, either the digital one that you can register for online and look up yourself, or you can get the photocopies in the Crim lab, which have the information. And what you'll see is that for uniaxial materials, you'll look up calcite, and you'll look up what epsilon is for calcite, and you'll look up what omega is for calcite, and you'll see, okay, what's epsilon minus omega? There's two actual values. And so if epsilon is greater than omega, then positive optic sign, because a bigger number minus a small number is a positive number. Whereas if epsilon is a smaller number than omega, then you'll get a negative number as a difference, and that'll mean it's a negative optic sign crystal. Okay, so this is one of the ways you can memorize how optic sign is determined. Okay. Now, the absolute value of this particular difference is a property called birefringence for uniaxial materials, and I will talk about a bit later, probably next time we see each other, when we start talking about biaxial crystals. Okay, but birefringence is a value for uniaxial crystals. The birefringence is defined as the absolute value between epsilon and omega. Okay, so we just talked about epsilon minus omega. You can determine the optic sign is a positive or negative just by making that calculation. But the actual value of that difference is a property that is a characteristic for that particular crystalline material. Okay, so that's a property called birefringence. Now we're going to move on to that indicatrix thing. Okay, so this is also directly from your the Dr. DeForest's chapter in the Forensic Science Handbook, and it looks kind of similar, right? It looks like there's an ellipse, and there's also a circle, or there's a circle, and inside of it's an ellipse. But this is the inverse thing that I was talking about, because the indicatrix figures are represented by the diameters in it are represented by the actual magnitudes of the refractive indices. So back to that idea, omega is the same in every direction. So the omega portion of the indicatrix figure will still be a circle, or in 3 dimensions it'll be a sphere. And the extraordinary ray, once again, it's going to be a different refractive index value depending on the direction in which it's vibrating, but that vibrational direction will be perpendicular to omega. And over here, we still see our optic axis up and down for both of these things. And we see a situation where we have omega vibrating in this direction. Remember what we said before? Omega vibrates perpendicular to the optic axis. So if you actually do have a situation where omega is vibrating, if you have the crystal set on the stage of the microscope in such a way that the optic axis is aligned with the illumination path, so the light's coming from the bottom, So the marker is going to represent the path of the light that's going to be hitting the sample. So in that particular situation, you'll have, no matter how you orient the crystal, remember it's only east-west when it hits it. When it hits the crystal, it'll go east-west and there'll be a north-south because it'll split into two mutually perpendicular vibrational modes for the light rays that go through. But as it turns out, both of them are going to be experiencing omega. Okay. The two rays, one vibrating this way, the other one vibrating that way, it's still omega. Okay. And that's one of the things that this particular diagram is showing you. So over here, epsilon is vibrating in this direction, and omega is vibrating in this direction, but we can just think of the two vibrating perpendicular to each other. And this diameter represents the magnitude, what's the numerical number of the value of epsilon. So that's a longer diameter than you have over here. And remember what we said, when epsilon is greater than omega, positive optic sign. Okay, when epsilon, this diameter, is bigger than that diameter, positive optic sign. Okay. When omega, the value of omega, the magnitude, which is represented by the diameters over here once again, omega is larger than epsilon, negative optic sign. Okay, back to that idea of how do I figure out the optic sign of a uniaxial crystal? Let me take epsilon minus omega. I can look up the values for those materials in the particle atlas. And if epsilon is a bigger number, epsilon minus omega is going to be a positive difference. Okay. If epsilon is a smaller number, like 1.8 minus omega, which is 1.5, I'm sorry, let's say 1.8 minus 1.9, then that's a negative difference, right? 1.8 minus 1.9 brings us into the negative part of the number scale, and that'll mean it's a negative optic sign. Okay. So indicatrix figures, they take a little bit more for you to understand because it's refractive index that the diameters are measuring as opposed to the velocities. How far did the light ray go in a specified amount of time? That's what the ray velocity surfaces are showing us. The indicatrix figures are showing us the actual magnitudes of the refractive indices in any particular orientation. So you guys, because you made the effort to come to lecture, and I appreciate that, because I teach to people. I'll give you the cheats for this. These indicatrix figures, I grabbed them right away. These are the uniaxial ones. How do I know? Because there's a metal rod going through them, okay? If you don't know to look for the metal rod, these two do not have a metal rod going through them. That's the cheat, okay? So if you knew nothing about indicatrix figures, at least you could be like, oh, metal rod. Those are the uniaxial ones, okay? Hopefully you do know something about them by the time we're done, and you'll be able to explain not only are these the uniaxial ones, but which one's a positive and which one's a negative optic sign. But if the ones that have the metal rods going through them, can you see what I'm talking about? That's a metal rod. That's a metal rod. If you see the metal rod is the axis. Uniaxial, one axis, metal rod. That's the axis. The one axis for the uniaxial. Same here. The metal rod represents the direction of the axis for the uniaxial material. Okay, and we'll get to biaxial later. Biaxial has two axes. Okay, so no metal rods for that, but those are the indicatrix figures that we're talking about. So the indicatrix is a 3D vector plot of refractive indices as a function of the direction of vibration. So now we're not even talking about the direction of translation, the light rays moving from here to there. We're talking about the refractive index and the direction it's vibrating in. Remember, it vibrates perpendicular to the direction that it's traveling in. Okay? So, as an example, let's say I've got this uniaxial material, and it's positioned just like this on the stage of the microscope, so that it's aligned, the optic axis is aligned with the path of the light that's going through the microscope. Okay? And remember, we've got our polarizing filter set up so that, the only light that it allows through that filter that's on the bottom of the condenser, if you've oriented it correctly, it's letting in light that's vibrating east-west. Okay? That east-west light hits my sample that's on the stage, and those rays split into two mutually perpendicular rays. Okay? And this is one of those funky situations where the teal-colored part of the indicatrix, it represents the omega refractive index. Remember, omega is constant. So whether it's this way or that way, it's the same value, which means that the teal, which is a circle, okay, it represents omega, but it's representing the vibrational direction of omega. The light's going up this way, and the light's vibrating like this, so it's experiencing omega, it's translating that way, it's vibrating this way, and indicatrix figures, the directions that we're thinking about when we're looking at these things are vibrational directions. They're not translational directions. You understand the difference? If I have like my light coming out of my laser over here, it's translating. Remember, translation is the movement from one place to another place. Like translation might be, I crossed the street, so I moved from here to there. I'm not really vibrating, I don't think. So I've got my laser translating from the tip of the laser to the wall to your left. But those light rays are also vibrating maybe up and down as they go that way, or maybe side to side as they go that way. Okay, because the light's moving in 3 dimensions. One of those dimensions, it's translating, and the other 2 dimensions is how it's vibrating. Okay, X, Y, and Z directions. So this is like a summary of how to distinguish the 2 kinds of figures that we spoke about. The ray velocity surfaces, 3-dimensional plot of velocity is a function of direction of propagation. So the directions there were the light's moving from this point to that point, whereas for indicatrix, the directions that we're talking about are vibrational directions. So you got to think about these.
I have a question. For those, is the slanted one an epsilon prime or?
Yes.
Okay.
Excellent. The slanted one is an epsilon prime, an example, and the slanted one is the yellow. Okay, so you've got the teal colored, which I don't know if you can see too easily just because depending on how the light's hitting it, but the circular section is teal colored. The red is an ellipse. So the red is representing epsilon and all the epsilon primes all the way to the point where the, so remember how we think about ellipses? We can talk about a minor diameter, which is in between my index fingers, is the shortest diameter in the ellipse, and a major diameter in between my index fingers, the longest diameter in the ellipse, right? Turns out that for this particular indicatrix figure, the major diameter of the red ellipse is equivalent to omega, the diameter of the circle, okay? Which means that this must be the value of epsilon. Epsilon is smaller than omega, negative optic sign. Okay, so these are the kinds of things which, like I said, the cheat is, oh, metal rods, uniaxial. And if you want bigger one, negative optic sign, smaller one, positive optic sign. But you'll probably be needing to explain it to the instructor when you do your cornoscopic exercises. Okay, so you can memorize the metal rod, uniaxial. No metal rod, biaxial. Okay, uniaxial, big one, negative, smaller one, positive. But why? Exactly what we were just talking about. So let's look at the flip side of it. We also have teal for this other one. Okay, it's a circle. It represents the vibrational directions of omega once again. It's a smaller circle. And we have our red ellipse. Okay, in fact, we have, for both of these, we have 2 red ellipses, right? This direction, that direction. So we have our red ellipses. And the red ellipse will be representing epsilon primes, and the yellow being an example of an epsilon prime, of which there can be, I guess, an infinite number if you really want to slice it thin, right? So we've got a small circle, and the circle represents the refractive index omega, because it's the same in every direction. And it looks like the minor diameter of the ellipse is equivalent to length to the circle diameter. The teal circle represents omega and its vibrational direction, okay? And the actual diameter itself represents the magnitude of omega. You know, what's the value of the refractive index? It's small. Epsilon can go, the principal value of epsilon is larger, and epsilon primes get smaller, 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 to the point where in between my index finger, this epsilon prime is equal to the diameter of the omega circle. So epsilon prime over here is equal to omega, which means this must be epsilon. Epsilon is bigger than omega, positive optic sign, based on definitions. Remember, the value of this, 2 minus 1, is still a positive number, positive optic sign. Whereas with this, the circle had the larger value, so the minor diameter of the red represented the value of epsilon. This value of red, the major diameter, is an epsilon prime, which happens to equal omega, the diameter of the circle. Okay. So, like I said, you're welcome to come and take a look at these things. I will bring them to the lab, so you can cogitate, like test yourself which ones are the uniaxial metal rod. Negative, positive optic sign, because we're going to get into biaxials. So, but they are useful because, like I said, you have to incorporate a bunch of definitions to understanding these 3-dimensional figures. You have to understand that we're talking about the diameters representing the actual values or magnitudes. How big is the refractive index? If it's a bigger diameter, it's a bigger refractive index. If it's a smaller diameter, it's a smaller refractive index. Okay, but the directions of that diameter, if it's this way, that means that's a vibrational mode that the light is experiencing. So if it's vibrating like this, it's translating like that. It's vibrating in this direction and it's moving in that direction. Okay. So indicatrix versus ray velocity. And if you spend some time looking at this, this was a situation where this is ray velocity, positive optic sign, indicatrix, positive optic sign. And notice how they're flipped over, where the ellipse is inside the circle if it's a ray velocity figure. The circle is inside the ellipse if it's a positive optic sign or an indicatrix figure. Okay. Back to the definition. Refractive index is equal to the speed of light, c, divided by the velocity of the light when it goes into the crystal, which will be smaller. It slows down. The more it slows down, the higher the value of refractive index. The less it slows down, the lower the value of refractive index. Okay? So refractive index and the velocity of the light ray inside of the crystal are inversely proportional. Okay? So bigger numbers for one means smaller number for the other. And then same thing over here. For our ray velocity figure, our circle was inside of the ellipse. Okay? This would be for a negative optic sign. Over here, the same negative optic sign material, if we're talking about the indicatrix figure, is flipped over, and my circle is inside of my ellipse. Okay. So back to that idea, omega is greater than epsilon, negative optic sign. And if we think about that in terms of how fast the light ray experiencing omega is going and how fast the light ray experiencing epsilon is going, this makes sense also. But you have to stare at them a little bit. You have to think, what's the definition? What does it mean to be able to get this? Because it's not like totally intuitive. It's not like you can stare and say, oh yeah, real quick. And if it is, then good for you. Because it's not the top one. When I first learned this, I was like, what? This is the kind of thing you have to spend time reading, thinking about, looking at these things, thinking again, maybe reading again, maybe reading a few different sources, and you have Dr. DeForest's chapter. You have the Polarized Light Microscopy book by McCrone and Belli. You have, I don't know if you have it, but I know that in the lab we have at least one copy, and I have a copy in my office of the Lost book, Optical Crystallography. And then that website that I've been using constantly with the Java tutorials, it also has information about all these different things, okay? So you have a lot of resources to read, and hopefully one of them like sinks in and it turns on the light in your head and goes, ah, that's what it all means, okay? So the ray velocity surface might be easier to visualize because you're talking about the direction that the light's traveling and how fast it's going, but the indicatrix is simpler and is more closely related to observable behavior. And so when we're talking about observable behavior, what we're talking about is, here's my crystal, it's actually on a slide on the stage of my microscope, it's already this big. And here I am looking through the oculars, and I'm gonna be measuring optical properties. And the optical properties that I'm measuring, they're actually, the values of those optical properties are related to these refractive indices in different directions. And that's why the indicatrix is more helpful, and that's why we're going to move forward talking about indicatrix. Okay. But first, let's talk about pleochroism. This is the, after you do the fiber exercise, you will do a pleochroid fiber exercise. So we should define what pleochroism means. But the chrome part is like color. Okay. Pleo is another way of saying many colors. Some people might refer to a fiber or another material as being dichroic, implying two colors. One color this direction, another color that direction, or a pleochroic implying many colors, although not many things are many colored. Okay, it's usually, and just as a heads up, when you guys start your hunt for your pleochroic fiber, I haven't yet seen a student find a pleochroic fiber that is literally two different colors depending on how it's oriented on the microscope. When you look for pleochroism, most of you, when you find your fiber, it'll be a difference in absorption, which means that when here's my slide and here's my fiber on the slide, when it's oriented like this on the stage, it looks dark blue, and when I rotate it 90 degrees, it looks light blue. That will be the pleochroism that you guys are more likely to find. Dark red and light red, dark green and light green. But tell me if you find one that's like, you know, blue and red, because it doesn't happen very often, okay? Because basically what's happening is that not only is the light experiencing a different refractive index depending on the orientation that the sample's in, it's also experiencing a different absorption of the light that's going through it. So not only refractive index is different, but absorption. So if it absorbs more, then it'll be darker. If it absorbs less, it'll be lighter. Just like black and white. Black absorbs all of this white light, it's dark, okay? White absorbs, reflects, it doesn't absorb the white light, so it's a lighter color. So you can think of absorption, the more that it absorbs, the darker it is, okay? The less it absorbs, when you guys are staring at these things, you're either looking at, with reflected light, it'll reflect whatever it's not absorbing, or through the microscope, it'll transmit whatever it's not absorbing, okay? So pleochroism is defined as the dependence of absorption or color on the propagation direction of the light. To exhibit this dependence, the material must absorb light or be colored. So you're not going to get a pleochroic fiber if it's white. So, you know, heads up, don't look for white materials to start plucking fibers off of. You need a colored material, you need a colored fiber in order to see something that might be pleochroic. If it's white, then you're not gonna see white and not white. Yes?
When you say colored, do you mean that it's naturally colored or can it be dyed?
It can be either, but it has to have a color. So it can have, you know, like I said, it might be some colored because of natural dyes, pigments, or it might be colored because the manufacturer put in a dye, put in some pigments, and gave it some color. Okay. And so a little bit of research, it's not too hard to start reading up a little bit. Certain fibers are more likely to be pleochroic than other fibers. So that'll give you the heads up, okay, I'm gonna look for this kind of fiber that's a color. I'm gonna start plucking fibers off of different things that are this particular kind of fiber and taking a quick look to see if I see pleochroism, okay? Okay. So with uniaxial materials, typically two principal colors or degrees of absorption. And the degrees of absorption, that's what I was saying, dark blue, light blue, or something like that. Okay. The material is said to be dichroic, di implying two colors or two extremes of absorption. So with the dichroic material, the absorption for the E ray and the O ray have to be different. So not only are the refractive indices experienced by the O ray different from the refractive index experienced by the E ray, so is the amount of the wavelengths that are being absorbed. So dichroism can be defined as differential selective absorption for the E and the O ray. Okay. So we already know we defined the E and the O ray as having different refractive indices unless the epsilon prime happens to be equal to omega. But what we didn't talk about is the possibility that in addition to the different refractive indices being experienced, those different rays will also experience a different amount of absorption of the wavelengths of white light. You have to find specific things that are dichroic or pleochroic. Many of the things that you do look for are not going to be. Okay. This is an example. I think tourmaline. Yeah, tourmaline is pleochroic. So if you ever looked at a tourmaline crystal, it'll look maybe a yellowish green color or a dark green color depending on the part of the crystal that you're looking at, and basically the whole concept of which directions the light rays are hitting it, which will give a different color. So examples of pleochroism, colored minerals show different colors in section. So over here, this is sort of like the yellowish green and darker green, or the possibility of yellow and green. And over here, the other example I gave you of light blue and dark blue. Okay. Most minerals change from a lighter to a darker color as the stage is rotated, which is what is being implied over here. Which is rotated. Each of these is being rotated 90 degrees. Okay, so it might be in this orientation, it's experiencing omega, rotated 90 degrees. Now it's experiencing an epsilon prime or epsilon. Okay, and it also happens to be experiencing a different color because the amount of the different amounts of white light absorption is different. Greater absorption for darker colors, less absorption for lighter colors. Thin slices of tourmaline were often used as polarizing filters before good synthetic filters became available. Okay. So polarizing devices, the nickel prism was an early type of birefringent polarizer. Nickel prisms produce a very high purity of polarized light and were extensively used in microscopy. And basically, I showed you the big old piece of optical calcite. They use smaller versions of these, and earlier this year, I got a bunch of different polarizers. There's all different kinds, apparently. But this is an example of a nickel prism. So it's a piece of optical calcite like this, okay? I don't know if you can see, but it's been cut down this diagonal over here. And Canada balsam, which is a material that's sometimes used as a mounting material for making slides. Canada balsam was used to cement the pieces back together after they've been cut. Okay, so let's talk about what that means. So it's a crystal optical calcite, cut, and then put back together in the same orientation it was before, except now you have a layer of Canada balsam inside of the crystal. Okay, that's the thing, glue it together. The crystal is cut in such a way that the O ray and the E ray are in orthogonal linear polarization states, okay, which they are anyway, right? Now, Canada balsam has a refractive index of about 1.55, and that's the material that's gluing the two pieces back together. Calcite, it's the omega refractive index is 1.66. Okay. Remember, omega is constant. With epsilon, it'll have different possible values. Okay. So total internal reflection. Do you guys remember what total internal reflection was?
Yeah.
Yeah. What is it?
It's when the angle of incidence is 90 degrees.
That's a critical angle. Yeah. Mm-hmm.
Yeah.
And then
And then
if you continue to increase the angle of incidence, it'll totally internally reflect. And that's basically the concept of fiber optics. Fiber optics, you're sending the signal, and it's being totally internally reflected inside the fiber of interest, which means that you're not losing a lot of information. You guys have seen that blue light kind of sheet sculpture that's in between the L2 and the L level. It's like not too far. It's like right if you're online for the J stop and you look behind you where the escalators are, there's this like blue, it looks like a sheet of blue fiber optics. Okay.
From the ceiling?
Yeah, it's
Oh.
like all wavy,
Yeah, I know what you're
right?
talking about,
Yeah?
Mm-hmm.
Okay, you've been to John Jay? So, and then you've looked around too, because if you don't know what I'm talking about, then maybe later on today, go to the L level, and it's it's more on the 11th Avenue side of the building, and then look at the escalators, and you'll see in between the L and the L2 level, there's like this blue-colored fiber optic sculpture. It's fiber optic, which means that the blue light is heading in one direction, and it's bouncing around on the inside of those fibers to make that net, and you're getting obviously some of it is escaping for you to see a blue color. But fiber optics implies that you have total internal reflection, or close to it, of the light that's inside of the fiber. So, let's see this review of, and total internal reflection was that extra credit from FOS 313, right? It's like, that's what it means, right? So let's say you got your glass. And you got air. And total internal reflection has to be when the light is inside of the more optically dense material already. Okay, so the light is inside of the glass. Here's the normal to the surface. And here is a light ray that's inside of the glass crystal heading towards that interface. And remember, as the light speeds up, it bends away from the normal. Right? So as the light exits the glass and enters the air is less optically dense, and so the light ray will bend away from the normal. And remember, it was the opposite way around. If it's heading in from the air, it'll bend towards the normal when it enters the glass. Okay, it's the exact same rule in terms of how is the light speeding up or slowing down. If the light is slowing down, it bends towards the normal. If the light is speeding up, it bends away from the normal. And clearly, the light cannot speed up faster than c, 3.10 meters per second. So the concept of total internal reflection means that at a certain critical angle of incidence, at this particular angle, let's see, critical angle of incidence, the reflected, well, the wave does not even enter the air. The refracted ray is actually at a 90-degree angle to the normal. Okay, so it goes from I sub c, and then, I guess, maybe theta c would be critical angle, and theta r is 90 degrees. Okay. If I have an even larger angle for the incident angle over here, I will get total internal reflection. The light will bounce off the inside of the glass and continue inside of the glass. And if you want to think of this as a fiber optic, which is not made out of glass, but the idea would be this is what's happening. Total internal reflection. So I'm not losing my cell phone signal or my telephone signal. I'm preserving a lot of that information as it bounces from one place to the other place in my fiber optics because of total internal reflection. Okay? I don't have stuff escaping outwards. So that was a little review of the physics of it all. Excuse me. Total internal reflection of the O-ray occurs at the balsam interface since it experiences a larger refractive index. See? Omega 1.66. So if we want to adjust, actually, I think I probably have the picture here. Yeah. So this would be the depiction of my nickel prism, okay? And it's going from upper right to left like that, okay? And as I send light through it, the light is entering, and you can think of this as like the east-west light, the light that's vibrating east-west as it goes through my polarizing light microscope, okay? The light enters, and when it enters, it splits into two rays, and they are vibrating perpendicular to each other. One of them is the O-ray, one of them is the E-ray. And remember, because they'll have E-ray, the E and the O, in most instances will have a different value, it'll mean that they'll travel different paths. One's moving faster than the other, one's bending more, one's bending less than the other. Same concept when it comes to refraction and the degree that light is slowing down, which will be related to the degree that light is bending, either towards or away from the normal. So I've got my two light rays over here now. I still have my light ray that's vibrating up and down. Over here it's the E ray. And then I have a light ray that is vibrating in and out of the screen, and that's my O ray. And the O ray happens to be hitting this Canada balsam interface. So remember, this is a different material inside over here. It's Canada balsam. It has a different refractive index. And because it has a different refractive index, the thing just like what I was talking about before, if you're going from a high refractive index to a low refractive index, and the angle is just right or larger than critical angle, you're going to get total internal reflection. And that's what's happening with the nickel prism. The light's going through. And so if you want to think of it this way, if this were going to be used in a polarizing light microscope, then it would be flipped over because you'd have light coming from the bottom of the microscope. It'll hit the bottom of the crystal, like that. And then the O-ray gets totally internally reflected and flies off to the side. The E-ray continues upward. And the E-ray will be the polarizing light that I will use to illuminate my sample. Okay? So I don't know if it helps at all. Just be careful with this. But this is the nickel prism. Yeah. So think about it. I mean, many of you have taken the microscopy workshop already, and it's a filter. I mean, it's a glass filter. This is like a flimsy plastic filter. We use, higher quality glass polarizing filters now, but that's what they used to use. That is a nickel prism that could have been used in a microscope set it up there, your light's going through it, and now I'm using that to create polarized light that will illuminate my sample. Sorry. It's like it's the music, the tone kind of emphasized the whole thing. Right? It's like so, the E-ray, which experiences a smaller refractive index, epsilon's about 1.49, is transmitted through the interface without deflection. This makes sense to you guys? Okay. That's how they used to make polarized light or get polarized light of just one direction. Because you send it through a crystal, you'll still have two rays that are vibrating perpendicular to each other. Let's just get rid of one of them by sending it all flying into space. That's the O ray, and the E ray is the one that we're going to use to illuminate my sample. And of course, then you would think of this is the optical path or the illumination path of the microscope. And since your microscope is not sideways, you can just flip it over and have light coming from the bottom. This would be coming from the bottom, going through the nickel prism. O-ray bounces off at the Canada-Balsam interface. The E-ray continues on, and that's the one that you're using to give you polarized light. And of course, you can adjust the positioning of your nickel prism so that you can have an east-west vibration mode or north-south or something in between. Okay. Moving on to more modern things like Polaroid film or Polaroid material. Polaroid material is also considered a dichroic material, and the idea would be to design a dichroic material to have a very high absorption in one direction and a low absorption for the other direction. Remember, absorption relates to color, so it's like very dark in one direction and then rotated 90 degrees and it's very light, a light colored in that direction. And basically would alternately appear black in one orientation and clear in the other when viewed in transmitted light. The idea of using a polarizing Polaroid film, which is kind of like what you have over here. You know, it's got scratched up because you know been passed around a bit, but that's the basic idea. So this material can be made in the form of an extensive thin sheet. It could constitute a very nice polarizer, and that's the idea behind Polaroid material, like the filters that I just showed you. The original Polaroid material that was used to make these polarizing filters for PLMs, orienting a large number of small crystals of iodine sulfate, apatite, and basically putting it on a cellulose hydrate sheet. So basically it's acting like one crystal. And then you stretch it so all the crystals are oriented in the same direction, and basically that's giving you your Polaroid material. So determination of dichroism. Once again, I will caution you, do not do your pleochroic fiber lab until after you've already learned everything you need to know about measuring optical properties for fibers during the fiber lab, in which case you'll be looking at like all these different samples: cotton, silk, wool, nylon, polyester, acrylic, monocrylic, acetate, rayon, all those different samples. When you're using the polarized light microscope, so that's your, let's say, filter in the bottom of your condenser, and then you have the analyzer that's in the intermediary tube, and usually if you don't, you can examine a sample, any sample with the analyzer out, okay, out of the field of view. When you look for a pleochroic fiber, you do not need the analyzer in the path. Because when you put the analyzer in the path, you get an interference color. I'm not talking about interference colors, I'm talking about colors that are a matter of absorption because of the light that's being used to illuminate it. Okay, by the time you put in something like this, and then you have some kind of crystal like this, you can see that. It's like a little bit of an experiment. Light's going through, light's not going through. And this is like a macro version of what you're actually doing through the microscope. But you'll be starting off by looking at fibers this way. Once you've And when you look at the fibers, it's the same idea. You'll start off by, you don't need the analyzer in the path of the microscope. You just want to put your fiber sample on the stage, and you want to focus it. Okay, so, and once again, you've already set up your microscope for Perler illumination. And then, okay, this is a piece of nylon. I'll put it on the stage of the microscope, start with low power so I can find that particular squiggly fiber easily. And then I'll flip up to higher magnification so I can get a good view of that particular nylon fiber. And then when I'm ready to, I can, and so maybe the nylon fiber will be a clear color. Maybe it's a white fiber, okay? Then I will put in my analyzer, and now the nylon, a number of things can be happening. The nylon might be totally black, okay, depending on its orientation. Or if it is totally black, this is my nylon fiber, I can rotate it and suddenly the nylon fiber starts to appear bright. And when it appears bright, there will be all these colors in the center of that fiber. And then when I rotated it a full 90 degrees, it's black again. And now it's bright. I mean, I could do it this way. Okay, so you can pretend this is what you're looking at on the stage of the microscope. If it's completely dark, then it'll be bright and colored, interference colors, and then darker, 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 black. And then the same thing happens when you do this. Total brightness, black. And in the bright in the bright position, when the sample is in a position where it appears bright through cross polars, you will see interference colors. And the interference colors you see will be a characteristic that you can measure. Measure what those colors mean. And the colors will, if it's a thick sample, and it tapers down to something like, let's say it's a cylinder. If the fiber is cylindrical in shape, that means it's the thickest in the middle, but on the sides it's the thinnest, which means that light is going through the thickest part of the sample and then thinner parts of the sample. The thicker the sample is, the more time the two rays have an opportunity to be heading in different directions. And you'll see a different interference color as opposed to where the light that goes through it is kind of, the fiber is thinner at the edges as opposed to at its center. So I'm going to show you some examples of that. So if the specimen changes color or degree of absorption on rotating the stage, it's pleochroic. And once again, I know we got rid of exercise numbers for this semester, so it's the lab after the fiber lab. The amateur mistake that people make is when they do pleochroic fiber lab, they have the analyzer in, and of course you're going to see colors. Those are interference colors. Those are not the colors of dichroism. Those are interference colors. Different thing, okay? So when you do your pleochroic fiber lab, when you first try to diagnose whether or not the fiber you plucked off of your backpack or you plucked off of some item of clothing or whatever the case may be, if you're trying to figure out if this fiber is pleochroic or not, you will have the analyzer out. You'll have the fiber, it could be air mounted, which means that take a glass slide, put the fiber on it and put a cover glass, no mounting material. You just want to get a quick idea because you don't want to spend a lot of time mounting all these fibers and 20 of them are not pleochroic and you wasted a lot of time. You could do an air mount, which means that you don't have to get the mount out or anything like that. Or you could do like a glycerol mount, which is real quick. But you can see pleochroism on a fiber that's sandwiched between two pieces of glass with no mounting material. You'll get a better view of it once you know that, oh, this is a good fiber. I'm going to take this one and mount it. Okay, but all the other ones that were not pleochroic, I'm just going to throw away. Okay, and the air mount is pretty easy. Examine the sample. In this orientation, oh, it's dark green. Rotate it. Oh, it's light green. I'm good. This is the one I'm going to use. As opposed to, it's dark blue. It's still dark blue. Chuck it. That's not pleochroic. Okay, it has to change in absorption And it might change in color, but not too many people find clear coke or dicoke fibers that totally different colors in the two orientations. And also bear in mind that by the time you're putting in your analyzer, in those orientations, they're typically experiencing what we call extinction, so they'll be dark anyway, right? So that's not the way to look at it. Okay. Yeah.
Why wouldn't we do the air mount? Why should we use a covered glass? Like, are there benefits to that?
Well, I mean, you want to use a piece of glass? What was that?
I mean, like, are there benefits to that, like, versus just putting it on the slide and just?
No, that's what I mean. Put it on the slide.
But you said to use like the cover glass?
So it doesn't blow away.
Oh, okay.
Yeah. Not only that, but one of the things, remember when I showed you at my workshop last week, remember I showed you that on the housing of the objective lens, it had the, 40, which meant that it was 40 times magnification. Underneath it, it had the 0.7, which was a numerical aperture. Underneath that, it had the 160 slash 0. What was it? 0.15 or okay. I'm having like a senior moment over here.
0.17?
Yes, she's correct. Extra points for her. 0.17. That 0.17 means that this objective lens was designed to be best used when you've got a cover glass of 0.17 millimeters in thickness. That's what the 0.17 means. So if you don't have a cover glass, it's not going to look. It's not. That objective is not designed to be used with just a sample slapped on a glass slide without a cover glass, right?
Yeah.
The 0.17 means that this objective lens was optimized to be used with a standard glass slide and a cover glass on top of sandwiching the sample of interest using some mounting material. And what I was implying before was you can rapidly test a whole bunch of candidates for clear acrylic fiber. Once you find the one that is clear acrylic, you have to mount it. Okay, you have to actually put the glass slide on a hot plate, get your melt, melt it, put your clear acrylic fiber on it, put your glass, cover glass on it, press down so that you have a nice even sandwich, and then you can take that sample and then put it on the stage of the microscope. Don't like get goopy stuff all over the place. Make sure it's a clean sample. And then you could do the optical property measurements of your clear acrylic fiber, because you'll be asked about things like, does it experience parallel extinction? And I'll define that in a little bit. What's its sign of elongation? And what's the absorption difference in the two orientations that you're observing it? Okay. If a polarizing microscope is not available, you can use a compound microscope, and you just stick one of these in the path of the light on the bottom. And you can actually just, those compound microscopes, you can't rotate the stage. You can just do that. And you can just do the same thing. But you guys will be using a polarized light microscope. Unless you come into the lab and it's busy and all the PLMs are being used and you're like, damn it, just get one of the compound microscopes that you use for microchemical crystal tests, and you can do that thing. But when it comes to measuring the optical properties of that clear acrylic fiber that you found, you will need to use one of the polarizing light microscopes. And one of the things I know that like a handful of you guys attended my workshop last Thursday. I only showed you how to use a BH2 microscope because that's the microscope you'll be using to get your practical on. We also have all those other microscopes, the Modic microscopes. They behave differently. The stage is not centerable for the Modic microscopes. The non-centerable objective is the low power, the 4 times objective. The BH2 microscopes, the stage is centerable, and the non-centerable objective is the 40 times objective. So slightly different. For the BH2 microscope, you push in the rod to get the analyzer into the path of the microscope. For the modic, you pull something out to get the analyzer into. So everyone has to take their workshop with the BH2 because that's what you're getting tested on. But you walk into the lab, all the BH2s are taken by your classmates. And you don't want to sit there waiting until someone's done. Grab a modic microscope if it's available. But then learn how to set up the modic microscope for curler illumination and do what you need to do with it. Like I said, we have a bunch of modic microscopes, and the whole idea is for you to be able to get your work done. Behavior of anisotropic materials in polarized light. As the sample is rotated between cross polarizers, I mentioned this before, it alternates between being dark and being bright, and it takes place 4 times during one complete 360-degree revolution of the stage. Plus there are 4 dark positions and 4 light positions, and then the intermediary as it's going from dark to brighter, 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 brightest, dimmer, 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 darkest. Okay. The 4 positions where the sample is dark, these are called extinction positions because all the light is being extinguished, extinction, okay? All light's being taken out of the picture. And the 4 bright positions are called positions of maximum brightness, okay? So extinction can only be defined for elongated crystals because if it's like this kind of parallel, oblique, or symmetric extinction, if your crystal is just like a cube, then it may well, remember cubic materials are isotropic, so they won't behave that way. But if your sample is an anisotropic material but happens to be shaped like a cube, it may well turn dark and turn light, but there's no reference for parallel and oblique extinction because these definitions require an elongated sample. If your sample is not elongated, then you can't say that it's getting dark in the elongated position if there's no elongated position, right? If it's just like a square, then it might be getting dark and light, but there's no reference for the long dimension of the sample and the short dimension of the sample, okay? That's what we mean when we say you need to be able to do this for elongated crystals. If it's not an elongated crystal, let's say it's a hexagonal crystal, for instance, then you can rotate a hexagon, but it's not longer in one, if it's a symmetrical hexagon, it's not longer in one direction than the other when you're seeing the dark and the light. Okay. So parallel extinction, the crystal will go dark while parallel to the crosshairs, the vertical and horizontal, the bullseye inside the microscope. The 2 vibrational directions of the crystal are aligned parallel and perpendicular to the long axis of the crystal. And the crystal exhibits parallel extinction, and it'll exhibit its greatest brightness at the 45-degree position. When the vibrational directions of the crystal are aligned with the privileged directions of the polarized analyzer, it'll appear dark. It's basically the same thing, I think. Okay, so this kind of explains it fairly well, and Java tutorial. So, stage rotation. So, parallel extinction, it's dark, it's bright. Take a look at the vector diagram on the bottom. What it's basically showing you is that in this position, the light's hitting, the light's going through the east-west orientation of the polarizer. So the light coming outside of the polarizer through the condenser is only vibrating side to side, east-west. That light hits your sample. It splits into 2 rays. And in this position, when the crystal is dark, what it's telling us is that the two rays, one of them is vibrating like this, and the other one's vibrating like that, okay? And as it's heading through the microscope, they'll end up getting blocked. So, analyzer polarizer, and now I've got maximum brightness, and then I keep going, and I get totally dark. Oops. I think it's straight up, but you get the basic idea. Light and dark. And now here, remember I kept showing you images in FOS 313 where instead of having a black background, it had this magenta colored background? You will be using something called the first order red plate. Even though it's more like a magenta or a purplish color. This is when the first order red plate is inserted into the optical path of the microscope. So if you recall, if you've taken your workshop, in the intermediary tube, the bottom of the intermediary tube has a turret where all the objectives are attached. And in the intermediate tube, there's a rod for inserting and removing the analyzer from the path. And there's also that little slot, which is at like a angle, and there's normally a blank black piece that is inserted into that with a hole in it, and the hole is supposed to be positioned so that the light can go through the hole, okay? And basically, you put your blank in there to prevent dust from getting into your microscope. When you're ready to measure optical properties of your samples, you can take out the blank, and in those kits, you've got 3 compensators. You've got the first order red compensator, which will make things look like that in the background. You've got your quarter wave compensator, and you've got your quartz wedge, which is literally a wedge of quartz, so it is what it sounds like. And as you insert it into the compensator slot of the microscope, the amount of quartz is thicker and thicker because it's a wedge. And what you'll also see is that it'll have an effect on the interference colors that you're observing. So, over here, just some of these things that you can look at, and if we have it out, oh, when we have it in, what are we seeing? Blue and yellow. So these are also interesting situations. When I don't have my plate in, I have a sample that looks like a low order gray. And I'll explain what I mean by low order. So it's a grayish color. And in some orientations, I'm getting, when I add this first order red plate, I get the background turns magenta, but my crystal went from being this low, like this mild gray color, like a steel gray, to blue, but as I keep moving, now I'm going to get extinction, and now I'm going to get yellow, okay? And this all has to do with the orientation of my crystal and the relative orientation of the crystal, and then the sample that you're inserting into the compensator slot. Its orientation is known, and you'll see it stamped on the compensators. And it'll allow you to make a diagnosis of positive or negative sign of elongation. And I'm going to explain that in a little while. But like I said, these are pretty useful Java tutorials. Okay. And this is basically showing you the exact same thing without being able to move things around. Maximum brightness position. It's getting dimmer, dimmer, and now it's in a position of extinction, okay? And it's extinction because the darkest position, the darkest the crystal looks is when it's aligned with the crosshair. If I rotated it so that it was aligned with the horizontal crosshair, it would also be similarly dark, okay? We call that parallel extinction. Oblique extinction occurs when the elongated crystal goes dark at a position between 0 and 45. So instead of being dark like this, it's dark at some other angle. And then as you continue rotating it, it gets bright and dark, but not at the same positions as you would see for a parallel extinction. Okay. What this tells us is that the vibrational directions within the crystal are at a non-90-degree angle with respect to the long axis of the crystal. And long axis of the crystal means the part where it's longer compared to. If this were my crystal, this is the long axis and this is the short axis. Okay, if this were a fiber, the fiber's length is like here, and this is the fiber's thickness. So basically that idea. Every single one of the fibers that you're working with, except for cotton, all but cotton exhibit parallel extinction. So when you have nylon, polyester, silk, acetate, monocrylic, in this position on the microscope, it'll be dark, maximum brightness, dark, maximum brightness. You get the idea. Cotton is different because remember when I showed you cotton in F1313, it's all twisted? And because it's twisted, parts of the cotton look dark while other parts of the cotton look bright. So as you turn the cotton a full 360, if you look at just one part of the cotton, you'll see it get dark and bright and dark and bright. But if you look at the whole sample, there's always part of the cotton that's bright because it's all twisted. That's the reason why you don't get extinction. You don't get extinction along the entire fiber of the cotton because it's twisted. If you untwisted it and flattened it out, then you would see like a better example of true extinction. But because naturally it's twisted, parts will look bright while other parts look dark, etc. But you'll see that yourself when you look at cotton through the polarizing light microscope. Symmetrical extinction occurs when the crystal goes dark at exactly 45 degrees to the crosshairs. The vibrational directions are at an angle of 45 degrees to the long axis of the crystal. So if this is the long axis of the crystal, then the vibrational directions are at 45 degrees to this. Okay. You will see symmetrical extinction in the spring semester when you make Teichmann crystals from blood. Okay. Teichmann crystals are a confirmatory test for heme, which is what we look for when we look to see if something is blood. So you'll be doing first like spot color tests, like phenolphthalein, leucomalachite green, and the glow in the dark luminol, chemiluminescence. But once you've mastered the color tests, then you'll move on to crystal tests. You'll be doing two of those. You'll be doing Takayama crystal preparation and Teichmann crystals. The Teichmann crystals, they look like little blades or those parallelograms or something like that. And Teichmann crystals are pleochroic, and they actually go dark at 45 degrees to the crosshairs. And so they'll be bright, and then dark, and then bright, and then dark. So they'll behave differently compared to the fibers that you'll be seeing in this semester. Okay, retardation, okay. It's like not a politically correct word, but okay, what does it mean? When a beam of polarized light falls on a uniaxial crystal at an angle between its two vibrational directions, this single direction is resolved into two mutually perpendicular directions within the crystal. And remember, we already talked about this. You know, the light hits the calcite, and it'll be resolved into two rays, one vibrating in one direction and the other one vibrating orthogonal to that. They will typically experience two different refractive indices, and so they will also be traveling different paths through the microscope. And you kind of saw that with the at the nickel prism that I showed you. The O ray is heading like this, and the E ray is moving in that direction because they're different refractive indices, which means they bend to a different degree through the crystal. One's going faster than the other one. So they experience different paths. And this is the part where this concept that we call retardation comes into play. After traveling through the crystal, these two polarized beams emerge vibrating at right angles to each other. Each of these beams has experienced a different refractive index within the crystal, and thus one has been slowed down or retarded with respect to the other one and emerges with a phase lag. Okay? They experience different refractive indices. Those two rays are traveling at different velocities. One of them went further than the other one. The other one was slower, lower velocity. And so even if the phases were we're talking about phase. This is my light wave. This is in phase. When the crest of one wave is aligned with the crest of the other. So this is in phase. Out of phase would be, and remember, you learned probably about total constructive interference and total destructive interference in physics. Does that ring a bell with you guys? Vaguely? If you geometrically add this, these two would add up to a wave that was twice the intensity, right? Whereas, I haven't done this real perfectly, but. The crest of this wave was aligned with the. Okay. So if you geometrically added this wave with that wave, you get no wave. Okay. This is total constructive and total, these two, total constructive, twice the intensity when they add together. But if you add this wave with that wave, you get zero, you get no wave. How about when you have a situation where it's like this? They're just not aligned. They're not perfectly in phase. They're not 180 degrees out of phase. They're just somewhere in the middle. Okay. So this is in phase, and this is an example of out of phase. This is also an example of out of phase. Okay. So phase lag, implying that one went faster than the other, and by the time they emerged, the crest of one was further ahead than the crest of the other one. It's like you have over here. Okay. This one, the crest is ahead of that one. Okay. The crest meaning the top peak of the wave.
So when, so if it's like that and you add them, what would happen?
Weird stuff. So, yeah, so with this, when you add the two waves that are in phase, you still get a sine wave, except the intensity is different, right? Yeah. Okay, if they're in phase. If you add this one with this one, you no longer get a perfect sine wave. You get a wave, but it's weird. It's weirdly functioned.
Like, does it have like a higher frequency?
You're not going to be changing the frequency of the wave. You're going to be changing its amplitude at various points. So, one example might be, let's say, and like I said, you know I measure all well. I'm going to show you some images of this in a little while, okay? But the basic idea might be you get weird stuff. That's what I mean.
Okay.
When you add things that are, and that's kind of exaggerated, but you get the idea. You don't get a nice sine wave where it's repetitive of a single wave, and you just repeat that. You just get weird stuff. Okay.
But the weird stuff that you get, is it predictable? Like, is it
Yes,
pattern?
it's totally predictable.
Okay.
It's just, it takes a lot more effort. Like what I showed you before with adding these two, minimal effort. You basically, that's plus one, that's plus one. You add them together, you get plus two and minus two. Plus two and minus two. You add this one to that one, you just get zero. Okay, but now if you have to make the effort of, okay, it's plus one here, but it's plus 0.3, then at that point in space, I'd add up to 1.3. Over here, I have like negative 0.2, but I have positive 0.7. So you're going to be getting, you could do the geometric addition of the two different ways when they're out of phase, but it just takes a hell of a lot more time because it's not the same as, plus one minus one becomes 0, or plus one becomes, 2, and basically, 0 plus 0 is still 0, right? Those were the easy ones. That's why they use them as examples when you learn about interference of waves in physics. But those are the easy things. You can have waves that are out of phase, You can have waves that have different amplitudes. And how out of phase are they? Maybe a little bit, maybe a lot of it. So all these different possibilities. So here is an example, and this is a really good depiction of how you're going to be looking at a sample through a polarized light microscope. So you've got your white light coming from the bottom of the microscope. It hits your polarizing filter, and in this particular situation, the polarizing filter is only letting light that vibrates in this direction through. And that's why you see this, okay? So, let's do it like that. Come on, Brianna, look at this. So, the white light comes through, and it's only letting light through that's vibrating in this direction. Now it hits this crystal, okay? It hits this crystal, and now the light that, that is illuminating that crystal, it resolves into two other light rays that vibrate perpendicular to each other. One of them is vibrating up and down, the other one's vibrating side to side. But not only that, these two light rays, the striped one and the solid one, they're also experiencing different refractive indices, which means that one of them will be moving faster than the other, which means that by the time they go through the analyzer, they will be out of phase. Okay, and the out of phasedness of this, it shows you that the crest of the striped one and the crest of the solid one, they're not aligned anymore. One of them is further away than the other one. Delta n times t, which means delta refractive index times time, okay, gives you the retardation. I'm sorry, not time, thickness. Thickness. And thickness is the thickness of the crystal here. So what's the difference between refractive index in this orientation, vibrating up and down? And the refractive index of light that's vibrating side to side? And the thicker the sample is, the more retardation there will be. That makes sense if you go by delta n, n1, what's the difference between n1 and n2? That's a birefringence, by the way, times thickness. And so it should make sense that if this is a thicker sample, and oops, look what we got here. Thick sample, thinner sample. So if I were to put these two, this one's like a little darker color. Okay. Both optical calcite, baby and mommy. Okay. Clearly, when the light's going through both samples, the light goes through a greater thickness of sample over here. And it means there's more crystal for the two rays to be experiencing different refractive indices. And even though they're both the exact same type of material, they're both calcite, it will experience different retardation just because the sample's thicker. That's why the T is important. It also means that exact same sample, but the retardation we're seeing is different, which will also mean a different interference color. And as a result, that's the reason why you see different colors inside of your fibers, because like I said before, the fiber, if it's cylindrical, it'll be thickest in the middle, and it'll taper off at the ends. And so it'll be like less of the sample at the ends, more of the sample. So, if this is my fiber, and I've got my light heading from the bottom of the microscope, and I mean, that's the direction of travel, and these light rays are vibrating east-west, right, because they're polarized. And so the light ray that travels through the center of the fiber, much greater thickness. Okay, so these two rays that are vibrating perpendicular to each other will experience a greater retardation because of a greater phase lag. Delta n is the same, T is different. However, a light ray that travels on the side over here, the thickness is smaller. So it's it's not as experiencing, it's experiencing less retardation compared to light rays that travel through the thicker part of the sample. Over here, even less sample, even less retardation. So delta N is still the same for the whole sample, but the T, the thickness of the sample, is different in the same sample just because it happens to be a cylindrical sample. Okay, so that's the reason why when you're looking at a sample, if this is the field of view, and you're looking at your, let's say, polyester is really cool, because polyester is highly birefringent, which means that you'll be seeing a rainbow of colors, multiple rainbows, from the center to the outside of the polyester fiber. And this doesn't do it justice, you're just seeing lines here, but you'll be seeing basically a multicolored rainbow, and it's symmetrical. If it's a cylindrical fiber, it'll be a symmetrical. You'll see one color in the middle, and then you'll see symmetry in the colors moving from the center to the edges. Okay, and that'll give you an insight into whether or not the fiber is actually symmetrical, cylindrical. So does this make sense to you guys? Okay. The delta N part is the birefringence of the material, and you guys will actually be trying to make a measurement of the thickness of the fiber, which is not easy to do. Okay. But you're going to make an attempt to do a good example. You can measure this, and it'll be easier to do that. When the fiber is oriented like this, and you've got your ocular micrometer in your right ocular. And then you can find out with this particular objective magnification, you can find out how many, like what does the distance between these two lines represent for the 40 times objective using a stage micrometer, and then use that information to measure how thick is this fiber like this. However, this works best if this fiber is cylindrical, right? But if your fiber is not cylindrical, then you're not going to be able to get a good measurement. Think about cotton. Cotton is like that ribbony thing, okay? So, oh my God, I can't draw well. Yeah, okay. I can't really draw it very well, but, so let's say this is a piece of my cotton. It's like a ribbon, but it'll twist along its length, okay? If I use my ocular micrometer, I can measure this, but this width is not the same as this thickness. And what I'm concerned about is the thickness of the sample that the light's going through, right? So you can't use the same method over here. What you could do is figure out, okay, if I look at a part of my cotton, which is like this, when I'm looking at the sample with a microscope, I can measure this thickness and then apply this information for further down the sample when it's flat. So I can get an idea that, okay, this cotton sample is about this thick based on measurements with the ocular micrometer that have been scaled based on the stage micrometer for that particular objective. But it's a little bit harder, okay? You have to take a little more time with that. Okay. So, retardation. We often refer to these beams as having taken different optical paths, and the amount of the phase lag depends on the difference in refractive index. Remember, we defined birefringence as a difference in refractive index, delta N, which could be like epsilon minus omega, basically that's it, and the thickness of the sample, the physical path. I think I'm pretty much at time with you guys. So, I'm going to leave it with this. I highly recommend that you do some